In this lecture, we are going to examine the differences between computers. Unlike PCs, PLCs do not have permanently attached devices such as keyboards, CD drives, or monitors. PLCs are designed for harsh industrial environments, where they must withstand wide ranges of temperature, humidity, and electrical noise. PLCs are typically programmed using relay ladder logic or one of several other standardized languages. The programming capability is built into the PLC's memory. A PLC executes one program sequentially, step by step, while a PC can execute multiple programs or tasks simultaneously in varying orders. In addition, software associated with PLCs, though often installed and run on a personal computer, can be broadly classified into two major categories. The first category is PLC programming software. This type of software provides engineers, technicians, and programmers with the tools necessary to create, edit, and maintain PLC programs. These programs are typically written in relay ladder logic, but other standardized languages, such as function block diagrams, structured text, instruction lists, or sequential function charts, can also be used. The software not only allows the user to write the control logic, but also to document the program thoroughly, including labels, comments, and descriptions of the control process. This documentation is essential for troubleshooting, training, and long-term maintenance of the system. The second category is called Human-Machine Interface, HMI, software. HMI software focuses on monitoring and controlling the process. It enables operators and engineers to view a graphical representation of the process on a computer or touch panel display. With HMI software, the user can operate machines, adjust parameters, monitor real-time values, view historical trends, and respond to alarm conditions as they occur. HMI systems greatly enhance the operator's ability to interact with the process and improve overall efficiency and safety. A PLC's architecture is similar to that of a personal computer. Both have a CPU, memory, power supply, and input-output handling. However, PLCs are specialized for industrial automation and control rather than general computing tasks. This ruggedness and modular design make PLCs far more reliable in manufacturing, power plants, and processing facilities. A PC would crash or fail under these conditions, but a PLC is purpose-built to keep critical processes running. Unlike personal computers, PLCs are programmed in specialized control languages. The most common is relay ladder logic, RLL, designed to look like traditional relay circuits. Relay ladder logic was developed so electricians and technicians familiar with hardwired relays could quickly adapt to PLCs. This makes PLC programming practical for industry adoption. External programming devices, like laptops with PLC software, are only needed to write or modify the control logic. Unlike personal computers, which are designed for multitasking, PLCs operate in a very different way. A PC can run multiple programs at the same time, for example, Word, Excel, and a web browser, and the operating system decides the order in which these programs are executed. This makes PCs very flexible, but the timing of execution is not always predictable. In contrast, a PLC is designed for deterministic and reliable control. The PLC executes a single program in a very orderly and sequential cycle. It always starts with the first instruction, works step by step through the program, and ends with the last instruction before repeating. This ensures consistent and predictable timing, which is critical for automation and industrial control. Looking at the execution cycle shown in the diagram, the process begins when the PLC monitors the inputs. It checks the status of all field devices, such as sensors and switches. Next, it executes the control program by processing the logic instructions step by step. Finally, it updates the outputs, which means it activates or deactivates devices like motors, lights, or valves. Once this cycle is complete, the PLC immediately begins the process again, continuously scanning in real time. This repeating cycle is what allows a PLC to respond quickly and reliably to changing conditions in the field. One of the key advantages of PLCs is how simple they make troubleshooting. Most PLCs include fault indicators and messaging displays that alert technicians when something is wrong. For example, status lights on the CPU can show whether the controller is in run mode, has a fault, or has a low battery. Similarly, output modules often have individual status indicators that reveal if a fuse has blown or if a particular channel is active. This built-in feedback makes diagnosing issues much faster compared to older relay systems, where troubleshooting meant physically tracing wires and connections. Another benefit is how easily input and output modules can be connected and replaced. Each module simply slides into the rack and connects through the backplane. If a module fails, it can quickly be swapped out without rewiring the entire system. These design features, status indicators, fault messages, and modular components help reduce downtime, improve system reliability, and make PLCs much more user-friendly in industrial environments. When we program a PLC, we use specialized software designed to both create and document the control logic. For Allen Bradley PLCs, the most common tools are RS Logics and RS Links. RS Logics is used to write the control program, often in ladder logic, and to fully document the process. This makes it easy to understand, maintain, and modify later. RS Links, on the other hand, is the communication software that allows the PC to connect with the PLC hardware so the program can be downloaded and monitored in real time. The most popular programming language is ladder logic, shown here at the bottom of the slide. Ladder logic resembles electrical relay diagrams, making it easy for technicians and engineers with electrical backgrounds to learn quickly. Together, this software allows us to both program the PLC and visualize how the system is functioning, which is critical for both operation and troubleshooting. This slide introduces PLC HMI software, or human-machine interface software. The HMI allows operators to monitor and control a process using a computer screen. Here, you see a steam power plant represented graphically. The operator can view pumps, turbines, and generators in real time, check system performance like steam flow or megawatts, and even watch data trends over time. Most importantly, the HMI alerts the operator with alarms when something goes wrong, making it easier to respond quickly. In short, the HMI is the bridge between the operator and the PLC, giving visibility and control over the process.